Hello, I'm your host, Khari Douglas, and welcome to Catalyzing Computing, the official podcast of the Computing Community Consortium. The Computing Community Consortium, or CCC for short, is a programmatic committee of the Computing Research Association. The mission of the CCC is to catalyze the computing research community and enable the pursuit of innovative, high-impact research. In this episode, I interview Dr. Mark D. Hill, Professor Emeritus of Computer Sciences at the University of Wisconsin-Madison. Mark recently joined Microsoft as a partner hardware architect. His research interests include parallel computer system design, memory system design, computer simulation, deterministic replay, and transactional memory. He is the Chair Emeritus of the CCC Council. In this episode, Mark discusses the importance of hardware security, the impact of AI on hardware, and working in academia versus industry. Enjoy. So we're here today with Mark Hill. How are you doing today?
I'm doing very good. It's a pleasure to be here with you, even though here is cyberspace.
A few years ago, you wrote a blog post about the Spectre and Meltdown hardware vulnerabilities. So could you just briefly explain what those are, and then has anything important in the field of architecture changed in reaction to those exploits? So
what Spectre and Meltdown showed was we thought we were designing computers that were looking like they were executing instructions one at a time, but actually going faster because underneath we guessed at what we were going to do next so that we could get that instruction level parallelism. We thought we completely covered our tracks when the guesses were wrong and no information would leak. But it turns out with some clever work, you can actually essentially use that speculation to leave some breadcrumbs that another gadget, it's called, can detect, and you can leak information. And this caused a big crisis. And industry has subsequently worked to mitigate this to significant degree, but as far as I can tell, not eliminated it. Academia is working very hard to come up with principal methods of eliminating this method of information leaking while still getting pretty good performance. And much of the formal work involves something called information flow tracking, which was originally developed for paying attention to classified data and how and who could see it. And so I think things are going to be better. This is a classic example where the abstraction of the hardware that it just executed instructions was not enough that underneath the implementation leaked. So it's quite an interesting thing. And the computers that you buy today are not completely cured of it.
So how much security work typically goes into the design and creation of computing hardware?
So I think this is a challenge is people buy computers mostly so that they're as fast as possible on the price. They may say they worry about security, but they don't as much. Hardware, the principal security has done is to try really hard to isolate the operating system from user code, and then more recently the operating system from a hypervisor. But it's sort of not fundamental to the design. And part of the problem is that the incentives are wrong. So if I, as a hardware vendor, made my hardware more secure, but 15% slower, it appears more customers would be concerned with the 15% loss in performance than they would the improved security, which is like hard to measure and know if you're really getting it. So we have a problem for security in hardware, and we certainly have a similar problem for security in software.
Do you have any thoughts on how to better align those incentives to improve security?
Well, that's a complicated process, and it turns out the Computing Community Consortium, as we speak, is trying to identify possible workshops to address this specific issue. There's a hardware workshop that's in a relatively mature state, and I think there's going to be a more general one. In other fields, you do things like industrial standards and even regulation. And those are heavy hammers, but we might need those hammers, or we might need the threat of those hammers to get better behavior, because the current situation is not working. And I blame we computer scientists, right? We built these computers half a century ago, assuming that security wasn't that important because this is a special. And, the track record of humanity is that in all domains, some notion of crime eventually comes. So it was naive of us to not think of that as a first-order consideration from the beginning.
Yeah. So you mentioned that the CCC is working in this area related to hardware and security. So how did you first get involved with the CCC and with CRA?
So back in about 2012, Ed Lazowska, who was one of the early people with the CCC and others, tapped me to run a sort of fast white paper with the leaders of a bunch of professional societies in computer architecture on what we should do sort of post-Moore's Law. And we wrote a white paper called 21st Century Computer Architecture. I think the whole process was less than 3 months. And subsequently, NSF cited this in a funding program that was $16 million a year, and in various guises, this has continued on to today. Since no good deed gets unpunished, the next year I was invited to join the CCC, and since I thought that was a fun experience with the white paper, I joined as a CCC member. And I guess I've had about a 8-year arc.
So obviously, Catalyzing Computing is the official podcast of the CCC, but for the most part, we don't really dive that much into the working of the CCC. But since you are the former chair, maybe you'd like to talk a little bit more about it. So what is the CCC and what does the CCC do?
Okay, so the CCC is basically an NSF-funded think tank of about 20, mostly professors, some from industry, complemented by some really great staff in Washington, D.C., where the two are greater than the sum of the parts. Our goal is to try to identify places where computing research ought to go and investments ought to be made. Finding the future is often hard, but what you can often do, William Gibson, the great science fiction writer, says, the future's already here. It's not evenly distributed. And so that's part of what we're doing. We get the experts together and we can articulate something and then spread it to many others, including funding agencies. And this is done through workshops where we're very good at getting a short white paper out of it. Sometimes it's standalone white papers. And there's ways when we partner with CRA Government Affairs to bring these things to the attention of government. And it goes back to the community through the publishing of the papers and the fact that it's the community that participated in the workshops.
So what would you say is your highlight of the time you spent with the CCC?
Well, the highlight probably has to be the 2018 AAAI CCC 20-year roadmap for artificial intelligence. Even though I was helping to catalyze this. I was chair of the organization and I played bad cop to help getting things out. Other people did the more work. So from the CCC side, Liz Bradley and Ann Drobness and others. But this was a really big deal, and it has already catalyzed and is referenced in some pretty significant NSF programs. And CRA Government Affairs shopped it around government, and I expect the biggest impact is to come. The key trick with AI was, AI is pretty hot in industry, so what do we need this roadmap for? And it turns out there are things that can complement industry from academia that can create a sum greater than its parts. These include often things that are longer term focus, and they can be issues that are maybe not industry's number one concern, like social justice may not be industry's number one concern, or maybe fairness is, maybe fairness isn't. But we could address things like that, and I think it's a very nice, albeit longer than I would like, document.
Yeah, I think it's over 100 pages, but people that are interested should check that out, and there will be links on the podcast webpage if you want to read more.
There's an executive summary that's way shorter.
That's true. So how do you think the proliferation of AI has impacted the hardware space?
So artificial intelligence has the potential to change a lot in society, hopefully mostly good. The current way it's done is, with the greatest successes, have been in a part of machine learning, which is a part of AI, the part of machine learning called deep neural networks. And these currently analyze a tremendous amount of data with a tremendous amount of computation. And if we could do that even more effectively, then machine learning could be used in even more situations. So a big step to greater effectiveness was moving from regular processor cores to general purpose GPUs, which did that data level parallelism that we discussed before. Now there's efforts afoot to do very specialized accelerators, as we've discussed before, for machine learning, such as Google's tensor processing unit. And I think we're going to see much more of that for deep neural networks. And then as AI starts expanding to other things, not just deep neural networks, I think it's important enough that hardware will be developed for that. Interestingly, there's a feedback path. We also have to design the hardware. And so there's some small new efforts on trying to take machine learning and apply it back to design and optimization of hardware to maybe make the human designers, instead of doing the design, they're doing the configuration of the AI to do the design. And so I think we could get a really nice synergy. I mean, you hear all this talk about AI, you might think it's hype, but it's pretty real.
Could you say anything more about Google's tensor processing units? I understand that's a pretty big deal within architecture when that came out.
Right. So the amazing thing is that tensor processing units are basically really good at multiplying a matrix, a two-dimensional array of numbers, times a vector, a one-dimensional array of numbers, producing a vector, running it through something called an activation function. That's doesn't really matter, a little Git widget, and repeating on tons of data. And we talked about ideas taking a long time. In the 1980s, there was this big thing called systolic arrays, called so because they had like a heartbeat and the data, like the matrix, moved around. And so these tensor processing units really are the mature outgrowth of that systolic array, just like GPUs were the mature outgrowth of the ILIAC 4 and other things from the 1960s. It can sometimes take a long time. And in this case, it was not only a long time for the technology, it was much more important. There needed to be an application that was sufficiently specialized and yet important. And machine learning has done that.
How much of your research involves the actual fabrication process of chips or hardware?
So I did fabrication of chips when I was a grad student, and I have largely not done it as an academic out of concern that I can't do it real enough. Other people have found that it's very useful to do it, so I wouldn't say that my approach is better. It's we like to have people doing different things. So I've used simulations and models mostly.
Okay. How does a simulator for a computer hardware system work?
Well, so a simulator is a software program that is sufficiently accurate that you can load application software on this software system, and it will allow the program to functionally execute and take a bunch of measurements, such as what the performance is. And it allows you to study a program executing on a system that doesn't exist yet. That's the good news, because you can change the system pretty easily because you're just changing the simulation software. The bad news is that this runs, depending on how you do it, 100, 1,000, or 10,000 times slower. So you can't really run the real workload. You have to do some very careful sampling. And if you do that wrong, like you just make something smaller, you may get an answer that's not correct. But it's exceedingly powerful.
Maybe this is a dumb question, but how do you know that the simulation you're working with is accurate or close enough when it doesn't exist yet?
It's not a dumb question, Khari. That's actually an excellent question. It's a very difficult problem. One thing you can do is you can configure the simulator so that it's very similar in one of its forms to an existing piece of hardware, and you can see if you relatively accurately predict what that hardware does. That's called validation. But it is harder to know for sure when you move off to hardware that doesn't exist whether you're completely correct. And one of the problems is that there's lots of hidden stuff in the simulator, so people can't just inspect all of it. And so sometimes these incorrectnesses can hide. That's one of the reasons why I like to complement things with models, because they can give you some detailed insights of what should happen. And if there's a divergence from what the model seems to be saying and what the simulation says, you can learn something. So, for example, Gables was used in a system. There were two examples where there's a simulation compared to the model. And in one case, in both cases, Gables predicted better performance in the simulation. So who's wrong? Well, it turns out in the first case, Gables made some assumptions about how parallel the workload was, which wasn't completely true. And so Gables was wrong. But Gables could be extended. But still, you get some insight. In the second instance, where Gables said a bigger number than the simulator, it was determined that there was insufficient buffers to really get the information flow that you needed. And if you fix those buffers, they match more closely, which it turns out is also an example of Little's law. There was not enough buffers to hold the intermediate state to get the full bandwidth. And so never trust sort of one way of looking at things. If you have more than one way of looking at things, you're more likely to have a robust answer. But you can never perfectly validate a simulator of hardware that doesn't exist.
Good advice. Are you involved with any other organizations or computing-related societies that you want to discuss?
Well, I've long been a member of ACM and IEEE. With ACM, I was an officer for a long time with the Special Interest Group in Computer Architecture, or SIGARCH. And, I'm old enough that I helped bring them into the World Wide Web age by setting up a web page where people could access information before search engines happened, and a monthly newsletter of web links so that people could find conferences and stuff. Some of those things you don't need anymore, but they were a big step forward at the time.
Yeah. So obviously you've been in a leadership role in many different organizations, and you're a pretty good public speaker. So do you have any advice or recommendations for people that are interested in taking on a leadership role within whatever organization that they're a part of?
Well, that's not an easy question. I think a couple things is to spend time reflecting on what you're trying to do, what your goals are, where you're trying to take the organization. But it's also, what's really important is you can't do that much yourself, right? The only way you can really get things done is to work with other people. And so you want to listen to other people, assess their strengths, get people, encourage them to do what they're good at, and try to get somebody else to do what they're bad at. and make sure that you're generous with credit, because it's very motivating when people get credit. And if you're running an organization, for example, you can give credit to all your people and they get credit, but you also get credit because the organization is running. So credit doesn't really divide, it multiplies in that situation. And I think people don't always appreciate that they're trying to grab the exclusive credit for themselves. And if you don't do that, you both make a lot of people happier, and I think you're ultimately more successful. So it's a win-win.
Yeah, it seems like good advice for sure. So let's see. You wrote a piece for Sig Arch's blog a while back about a vision of computer architecture. And the CCC, one of the things we do a lot of is quote unquote visioning. So what do you mean by visioning, and why do you think that's important?
Yeah. So, by the way, the title. You didn't get the title exactly right. It was a vision of computer architecture visioning. Well, it really was trying to articulate what the CCC does, right? And visioning is important because you want to get people to think about what the important problems are out there, and so that they work on the important problems, not the easiest problems to work on. The easiest problems to work on is you've just written a paper, like you just did LogTM. Well, let's do a follow-on paper on LogTM. Well, that's only important if the follow-on paper, is fixing a problem that people care about. And sometimes people get into the mode where they're just writing follow-on papers, even though people don't care. And so visioning forces you out of your box, talks to other people. You find that future where it's unevenly distributed, and you may go work on more important problems.
So I guess what would you say is the key to finding key problems to envision, or just key problems in general to do research in?
By the way, many people think the key job of a researcher is to solve problems, but the key job of a research leader is to identify problems, which is what you're asking about. And I have found the best place to identify problems is to look for change. Because if there's been no change, there's a good chance the problem is either unimportant or really hard. And I'm not that smart. And so I want to look for change so I can get an easy problem that has just emerged as important. So in computer architecture, change happens because the applications change. Deep neural networks are way more important than they used to be. It can change because the technology changes. There's this new stuff called non-volatile memory that is changing computer systems. Or it can change because tools change. There's things like SAT solvers, which make certain optimizations possible that were not before. So if you look for change, you may be able to identify places where if you can do it, people will care. You then have to complement that with, you want to make it likely that you can do something about it, right? Otherwise, it's a nice problem, but you don't make progress. And so that's what I find using models and to think about things. And I like taxonomies too, where I try to divide up the space into different quadrants, like the 2x2 table that you mentioned in LogTM. The ultimate, by the way, taxonomy is Mendeleev's taxonomy, periodic table of the elements, which organized things by atomic number and caused people to say, wait a second, we know of no element there, let's go look for it. And so that's a long answer to your question.
Yeah. So as was mentioned in the intro, you're moving from academia to industry, moving to Microsoft. So what prompted this change after a career in academia?
Right. So I had 32 years at Wisconsin, as various levels of professor and then department chair. And then I was chair of the CCC. And I had the opportunity to go back to being a professor again. I was always technically a professor, but primarily a professor. And it seemed like I could do that, but let's take a new challenge. And industry is particularly interesting now for much of computer science, especially computer architecture, because with the slowing of Moore's law, we have to find other ways to make things go faster. And that often will involve optimizations that cross many layers, which I'm relatively good at. 20 years ago, 30 years ago, it was all about optimizing your own little piece. And, that's just not as exciting to me. So now we have this opportunity and the necessity to optimize across layers. So, for example, systems like Microsoft Azure and other cloud computing systems, these have evolved from being a building full of server computers to being a computer in their own right. I mean, Luis Barroso of Google calls this warehouse scale computing. And so it's just a very exciting time, I think, to put some of my years of research experience to the sort of test of what the real engineering constants are going forward. But it's really more a personal thing, just to do something different instead of the same thing again.
So what are the tensions you've found in your career when it comes to industry and academia collaborating on the same problems?
So the tension is that industry and academia have different interests, although they have substantial overlap. I mean, industry really needs to make a money, and so they have to have a focus that's in the several year time frame, and they have to operate in many constraints. The instruction set of Intel processors is going to be x86. That's not a factor. Whereas in academia, you have other goals. You want to take a lot of risk. You want to look far. You want to push the envelope. You want to educate the student and get great publications. And so it's a little different, but there's a lot of overlap because both sides can teach each other a lot. Industry can help you know what problems are real, and academia can study them more carefully sometimes than industry can when they just need to make a binary decision, not really characterize things. And so there's a tension. The other tension is with intellectual property or patents. You have to be careful to figure out in a collaboration who owns the patents. Do both own the patents? That may be a little bit unfortunate, but that's U.S. law.
I noticed a presentation on your website where you mentioned that you've done 3 industrial sabbaticals in your career. You described them as high cost and high reward. What were those costs and what were those rewards?
So the cost is that you move, and often with a family, to a different place, and you devote a substantial fraction of a year to working for a company, maybe keeping your university activity going with 1 day a week. And so it can hurt the university activity. That's the cost. The benefit is you get embedded in a milieu that has problems. And some of those problems are very short term and they're being solved. Never mind those. Some of them are just emerging. They're not yet important enough. They're being band-aided. And some you can intuit from the technology change. And so you can come back from industry with new problems. That's the key reward. You can't come back from industry with new solutions because that's their intellectual property, but you can come back with problems. And the sabbatical is a high cost way to do it because it costs a whole year. Lesser cost ways of doing it are having industrial affiliates meetings or have a student, go for an internship.
So as we wrap up here, what do you think will be the most important area of computing research over the next 10 to 15 years?
I think it's twofold. On one hand, artificial intelligence with machine learning may be broader than deep neural networks. We'll see. It will have a profound effect on society, and that we need to shape that and follow our country's values. This is a big deal. People are going to say, self-driving cars, they told me I was going to have that by 2018 and it didn't happen. They're never going to happen. This is a classic example of the Gartner hype cycle where in the short term, people think it's going to happen and then it doesn't. You reach a trough of despair and it can come back. And I think that's true. AI is definitely doing a lot of things. It doesn't do everything it promises, but it will have a profound effect. And so systems supporting AI are going to be a big deal. The other side is that when I started, computers were in rooms. They were very isolated from people. And now, you have computers on your body, right? And you can have more computers on your body going forward. And you might have robots in your life. And so computers are going to be interacting with people in very deep ways. For example, people may have emotional attachments to computers. And I think we need to have a much deeper understanding of humans interacting with computers to make those computers more effective and serve humans in a good way.
Yeah, I think that will definitely be important going forward. Is there anything else that we didn't cover that you wanna bring up?
Well, I just want to say thank you to Khari. I mean, this is a good example of how it's great. Diversity by generation and career stage is a good thing, right? I can't run a podcast. You can run a podcast. I have some thoughts, and together we produce something that we couldn't do separately. So I really encourage all organizations and all collaborations to seek diversity in many different dimensions.
Sounds good. Well, thanks for taking the time to sit down with me. Have a good day.
Thanks.
That's it for my interview with Mark Hill. We'll be back soon with new episodes. Until then, remember to like, subscribe, and rate us 5 stars wherever you get your podcast. Learn more about the work of the CCC on our website at cra.org/CCC, and find us on social media to stay up to date on all our latest activities. Till next time, peace.